A star is dying. For millions, perhaps billions of years, it has burned with unimaginable power, a colossal furnace in the void. But its time is up. The fuel that held it aloft against its own immense gravity is gone, and now it is falling in on itself, fast, too fast. This should not be happening. To understand this moment, we have to look deep inside. A massive star is like an onion, with layers of different elements. On the outside, hydrogen fuses into helium. Deeper down, helium fuses into carbon, carbon into oxygen, and so on, creating heavier and heavier elements. Each stage of fusion releases a torrent of energy, pushing outward and creating a delicate cosmic balancing act against the relentless inward crush of gravity. But this process has a final fatal limit: iron. Fusing iron doesn't release energy, it consumes it. The star has created an anchor of ash at its heart. The furnace has gone out, and with nothing to hold it up, the star begins to die. At its core, everything collapses. The outer layers, containing thousands of times the mass of our own sun, begin a catastrophic freefall. They accelerate inwards at an almost unbelievable speed, 70,000 kilometers per second. That's nearly a quarter of the speed of light. An object the size of Earth is compressed down to the size of a city in less than a blink of an eye. In this final, violent moment, the force that has governed the star's entire life takes complete control. Gravity wins. The core crushes itself, squeezing protons and electrons together to form a sea of neutrons. It becomes so dense that a single teaspoon of this material would weigh billions of tons. It has reached the consistency of an atomic nucleus, a state of matter so extreme it can be compressed no further. It has become a proto-neutron star. In that moment, something critical happens. The collapsing core doesn't just stop, it rebounds. Like a cosmic spring loaded with the mass of a sun, it bounces back. A shock wave is formed. A titanic wall of energy and pressure, born from the core's rebound, begins to tear its way out of the star. This shock wave is supposed to destroy the star. It carries more than enough energy to blast the outer layers into space, seeding the cosmos with the heavy elements forged over millions of years. This should work. It's textbook astrophysics. The result should be a massive explosion, a supernova, an event so bright it can outshine its entire galaxy. But there's a catch. As the shockwave plows through the dense, infalling layers of the star, it loses energy. It's like trying to run through a hurricane. The sheer weight of the star falling inward is too much. And so, most of the time, it fails. Something goes wrong. The shockwave stops. It stalls out, frozen in place. Just 100 kilometers from the center, a tiny distance in cosmic terms. The star is now in a state of limbo, balanced on a knife's edge between a glorious explosion and total oblivion. And then, a countdown begins. A silent, desperate race against time. Scientists say there is a window, a tiny fraction of time for the explosion to be revived. The star's last hope comes from a flood of ghostly particles called neutrinos, pouring out from the ultra-dense core. They carry away almost all the energy of the collapse. If just a small fraction of these neutrinos can be absorbed by the material behind the stalled shockwave, they can reheat it, giving it the push it needs to finish the job. But if the explosion doesn't restart in less than 1 second, everything collapses. The window of opportunity slams shut. The weight of the infalling star becomes insurmountable. No explosion, no light. The star simply winks out of existence. The entire star, its stalled shockwave, its neutron core, all of it falls inward, crushed by its own gravity beyond the point of no return, and disappears into a black hole. But here's the problem. The great cosmic mystery. We don't know what decides it. We don't know the secret ingredient that tips the scales. Some stars recover. Their shockwaves are reborn, and they detonate in a spectacular supernova. Some stars don't. They become what astronomers call failed supernovae, vanishing without a trace. Even worse, when we try to model this critical moment, when we throw all of our computational power at the problem, our most advanced AI simulations can't predict it. Reality refuses to match the model. We can create simulations that explode, and we can create simulations that collapse. But we don't know for sure which path a real star will take. The models are incredibly sensitive. A tiny instability, a difference of less than 1% in the initial conditions, in the turbulence or rotation of the star, can destroy the explosion completely. In simulations, the delicate balance is easily broken. Energy jets that should power the explosion twist and break apart. They flail wildly, like a garden hose spinning out of control, dissipating their energy uselessly into the chaos. The explosion fails, but in reality, some stars explode perfectly. They overcome the odds, creating beautiful, almost symmetric remnants that enrich the universe. Others vanish forever, leaving behind nothing but a warp in space-time. Same physics, same conditions, different outcomes. It's one of the biggest unanswered questions in astrophysics. Maybe something fundamental is missing from our understanding. Some subtle aspect of turbulence, some quirk in the behavior of neutrinos, some unknown property of matter at the edge of existence. So what decides it? What happens in that 1 second? Because in that moment, in that single fleeting tick of a cosmic clock, a star either lights up the universe, writing its name in fire across the heavens, or gets erased from existence, its light, its matter, its entire history swallowed by the dark.